Hi. In this session, we discuss about the group action on set. The action of a group on a set details how set transforms under the symmetry described by the group. One way of thinking of a group G acting on a set X is that the element of the group G may be applied to elements of X to give a new element of X. Many problems in algebra may be tackled via group action. Let us see the definition of group acting on set. So let X be any set and G be a group. So it is not necessary that X is related to G. The action of G on X is defined as, or it is a map star from G cross X to X given by the ordered pair G comma X goes to star of G of X, G comma X. And it must satisfy the following properties. The first one is star of EX is equal to X for all X and X, where E is the identity element of G. And the second property is that star of GH comma H is equal to star of G comma star H comma H for all G and H belongs to G and X in X. If G act on H, then X is called a G set. As we know that if the group operation is not specified clearly, then we always take the group operation as multiplication. Similarly, in the group action, if the star is not defined, we define star of G of X as G into X. That means by the left multiplication. Note that, it's not necessary that in the group action, we are not requiring H to be related to G in any way. But it is true that every group G acts on every set X by the trivial action. That means trivial action star of G comma X is equal to X. This will be true for any X and any G. But the group action are more interesting if the set is somehow related to the group G. Let us see some examples of the group action. So let G is equal to GL2 of R. All of you are familiar with this group, and it is the set of all invertible matrices, 2 by 2 invertible matrices over R. And X is equal to R2, which contains all the ordered pairs. We think of the elements of X as the column vector, X1, X2. Then we define star from G cross X to X as star of A comma X, where A is a matrix and X is a vector which goes to A into X. And let us see whether this one X, the G acts on X. So to see that, we have to check whether it satisfies two properties. The first one is, you take one identity element of G, that is your it is I2, and one element from X. So you can see that then star of I2X is equal to I2 into X, which is same as X because I2 is the identity matrix. So the first property satisfies. What about the second one? For that you need two elements from G. So here we are taking A and B belongs to GL2 of R and X is in X. Then by definition of star of ABX is equal to A into B into X. Because you know that the multiplication is associative in matrices, we can write that as A into BX, or which we can write it as star A comma BX. Since BX is star of B comma X, I can write it as star of ABX is equal to star A comma star B comma X. So it satisfies the second property also. That means G acts on X. And here the star is defined by left multiplication with the element of G. Let us see the another example. Let H be a subgroup of G. So all of you are familiar with the set of left causes of H in G. So let us take LH is equal to the set of all left causes of H in G, that is our X. So we define star from G cross X to X by star of G comma XH is equal to GXH. We'll check whether this one is a group action on X, which is equal to LH. That means the set of all left causes of H and G. For that we need the identity element of G, E, and one element of X. Let us see it. Let us take it as XH. Then star of E comma XH is equal to E into XH. Because E is the identity element, EX is equal to H. So we have EXH is equal to XH. So it satisfies the first property. What about the second one? For that we need two elements from G. Let G and G dash belongs to G and XH belongs to X. That is LH. Then by definition of star of G G dash XH is equal to G G dash into XH. By the associativity property of the elements of the group, we can write it as G into G dash XH. But that is same as star of G comma G dash XH. But G dash XH is same as star of G dash comma XH. So therefore it satisfies the second property also. So thus G adds on LH via the left multiplication. So let us see another example. Let G be a group and H is equal to G itself. So we define the map star from G cross G to G by star of G comma H is equal to GSG inverse. This also a group action. For this, to check whether this one is a group action, we need to check two properties. The first one is we take identity element of the group G, E, and one element of X. Here X is equal to G, so X is also belongs to G. Then by definition star of EH is equal to E inverse, which is same as X. Let G1, G2, so it satisfies the first property, so let us see the second property. Let G1 and G2 in G and X is also in G because X is equal to G. Then star of G1, G2, X is equal to G1, G2, X, G1, G2 inverse. But we know that G1, G2 inverse is same as G2 inverse, G1 inverse. And using associativity, one can write G1 into G2H, G2 inverse into G1 inverse. So it is look like G1H, G1 inverse, but by definition that one is same as star G1 comma X. So we can write here it as star G1, G2H, G2 inverse. But G2H, G2 inverse is same as star of G2H. So we can write star of G1, G2H is equal to star G1 comma star G2 of X. So this action we call it as the acting on G acts on itself via conjugation. This is important to us in the future part, in the later part. So now we can see that this group action induces always a group homomorphism. So suppose, we state it as a lemma, let G be a group and H be a set. And we want to show that G acts on X if and only if there is a homomorphism phi from G to Sx, where Sx denotes the group of all permutations of the elements of X. Now, Sx denotes the group of all permutation of elements of X means what? It's a map. Elements of Xx are maps. In fact, it is the permutations. Permutations means what? They are all bijective maps from X to X. So that means that whatever be the element of G in G, phi of G is a permutation on X. That means phi of G is a map from X to X, which takes some element of X to some other element of X or itself. We'll see the definition of, see the proof of this lemma. So one way, suppose G acts on X. So here the action star is, by default we define it as the left multiplication. So using this action, we define a map phi from G to Sx by phi of G of X is equal to Gx. Note that G belongs to G, then phi of G is an element of Sx and it must be a permutation and it takes X to Gx. So we show that this, in fact, for any G in G, phi of G is it belongs to Sx? That means is it a permutation on X? Or is it a bijective map on X? To check whether that one is a bijective map, we need to show that it is onto and 1, 1. First of all, we will check phi of G is onto. So since phi of G is a map from X to X, we take some X belongs to the codomain X. We want to find a pre-image of X in the domain X. So since G acts on X and G inverse is belongs to X, G inverse belongs to G and G acts on X, we get G inverse X belongs to X. Therefore, by definition of phi of G of G inverse X is equal to G into G inverse X, which is equal to G inverse into X by the property of the group action and which is same as Cx, which is equal to X. So therefore G inverse X is a pre-image of X. So therefore phi of G is onto. Now to check whether this one is 1, 1, suppose phi of G of X is equal to phi of G of Y for some X and Y belongs to X. Then by definition, Gx is equal to Gy. So applying G inverse on both sides, we get G inverse Gx is equal to G inverse Gy. Now applying the second property of group action, we have, which is same as Gg inverse X is equal to Gg inverse Y. But Gg inverse same as identity, so we have Ex is equal to Ey and which implies X is equal to Y by the first property of the group action. So therefore, phi of G of X is equal to phi of G of Y implies X is equal to Y. Therefore, phi of G is 1, 1. Now, we have to check whether this phi is a group homomorphism. That means we have to show that a phi of G1, G2 is equal to phi of G1 composite phi of G2 for any G1, G2 in G. So let us take two elements G1 and G2 belongs to G and X belongs to X. Then, by definition of phi of G1, G2 of X is equal to G1, G2 into X. But by the second property of the group action, we have G1, which is same as G1 of G2X, which is equal to phi of G1 of G2X, which is same as phi of G1 or phi of G2X, because G2X is same as by definition phi of G2 of X, which is same as phi of G1 composite phi of G2 of X. This is true for any X belongs to X. Therefore, phi of G1 G2 is equal to phi of G1 composite phi of G2. Hence, phi is in a homomorphism. So now we prove the converse of this lemma. Conversely, suppose we have a map phi from G to Sx and which is a group homomorphism. We want to get a group action of G on X. So for that we define a map star from G cross X to X by star of G comma X is equal to phi of G of X. Because phi is a homomorphism, phi of E is an identity element of Sx. That means it is a trivial permutation. That means it is a phi of E of anything is equal to that thing itself. Therefore, for any X belongs to X, phi of E of X is equal to X. That means star of E comma X is equal to X. So therefore the star satisfies the first property. Also, as phi is a group homomorphism, by definition star of G1 G2 X is equal to phi of G1 G2 of X, which is equal to phi of G1 composite phi of G2, because phi is a group homomorphism. Phi of G1 G2 is equal to phi of G1 composite phi of G2 of X, which is equal to phi of G1 of phi of G2 of X, that is same as star of G1 of comma phi of G2x, which is equal to star G1 comma star G2x. Therefore, G adds on X. So this is all for the day. Thank you.